Hello friends, today we will discuss an experiment based on photoelectric effect. The aim of the experiment is to determine Planck's constant and work function using photoelectric effect and to verify inverse square law of radiation. So let's have a brief introduction. Photoelectric effect is the phenomena of ejection of electrons from a metal surface when light of appropriate frequency falls on it. It was first discovered by Heinrich Rudolf Hertz. Then relation between light and electron was clarified by Philip Lenard. Further research showed that photoelectric effect represents an interaction between light and matter that cannot be explained by classical physics, which believed that light is an electromagnetic wave. The major puzzling observations were that kinetic energy of released electrons does not vary with intensity. And secondly, there was virtually no time lag between arrival of radiation and emission of electrons. This led Einstein to formulate in 1905 a new corpuscular theory of light, which believed that light is made up of small packets of energy known as quanta or photon. Energy of the photon depends on frequency, not on intensity. By a relation, E is equal to h nu. Einstein was honored by Nobel Prize for this discovery in 1921. Einstein summarized his observations in form of an equation. So, which says that h nu is equal to half mv square plus E phi, where h is the Planck's constant and nu is the frequency of the photon, and half mv square is the kinetic energy of the photoelectron which is emitted out, whereas phi is the work function of the material from which the photoemission is taking place, and this is the energy required, minimum energy required to eject out an electron from the metal surface, and half mv square is the kinetic energy. So if a photon of energy h nu falls on a surface, energy of the photon h nu is used up in two ways, that is to eject it out from the metal surface, which is E phi part of it, and then to impart kinetic energy to the electrons emitted, which is equal to half mv square. Then we can also write half mv square is equal to h nu minus E phi. So here we can say that if we apply a negative potential at the anode, so that will apply a repulsive force on the electrons which are coming towards it, that is the photoelectrons. So if we can go on increasing that negative potential at that plate, so even the electrons which are moving with highest kinetic energy will not be able to reach that. So that particular potential is known as the stopping potential, and that is equal to half mv square, better half mvx square, v max square, that is the maximum kinetic energy is equal to evs, and that time the current will be equal to 0. So here I can write, substitute for I have half mv square, that gives me evs is equal to h nu minus E phi, or it can be rewritten as vs is equal to, that is stopping potential, is equal to h upon E nu minus phi. So this is a straight line equation. So if we draw a graph vs versus frequency, that is stopping potential versus frequency, so as it is suggested by this equation, it should be a straight line, and that straight line will intersect the x-axis at a point which is known as a threshold frequency, and if extended it will have an intercept on y-axis in negative direction, which will be the work function as suggested by this equation. So we can find out the work function from there, whereas the slope of the equation will be equal to h upon E. So the Planck constant h can be calculated as slope into E. So this is our experimental setup. So we'll know about the setup, and then we will see that how to perform the first part of the experiment. So this is our photo sensitive device. A vacuum photo tube is kept inside it, which contains a photosensitive material, and this is option given for applying the filter. So whatever filter we apply here, only that frequency is allowed to fall on that photosensitive material. This is a display unit. We can display current as well as voltage on this unit. So if the knob is on the right hand side, it displays voltage, whereas if the knob is on the left hand side, it displays the current. Then we have this current multiplier, so we can put it at according to our need, 0.001 or 0.01 or zero point 0.1 and so on. uh, then we have this intensity controller switch, so it can switch off or increase the intensity of our light source. The light source is a halogen tungsten lamp which emits all the frequencies. Then we have a voltage adjusting knob, so we can change the value of voltage with the help of this knob. We can increase or decrease it by moving it in anti-clockwise or clockwise direction. Then we have this commutator, and then this switch, which if it is on the right hand side, it is negative, and if it is on this is positive. We have this indicating lamp, and this on off switch. This is the light source. This is our light source. So it emits out light of all radiation, all frequencies. When we put filter, so only that frequency is allowed to fall on it. Now we'll see that how to perform the first part of it, that is to find out h and phi, Planck constant and work function. For that, what we do is, one more thing, we have a set of filters here. We have 5 filters here, red, orange, green, yellow and blue. So we can put them one by one. So to find out the stopping potential, what we do is, we put a filter here, and then we switch on the current light source. The voltage knob is kept at negative because we have to measure the stopping potential. Then we will put this display into the current. So what we have to do is, we have to increase the voltage which is in negative direction such that the current becomes 0. So we can we will change the voltage by the voltage knob. It is already negative, and then look for the current. Wherever we will find that it is 0, we will, this is 0 now. So now we will flick this button to voltage, and then see, this is the voltage, so it is minus 0.27 volt. So this is the voltage for this particular stopping voltage for this particular filter. Now what we can do is, we can remove this filter and put another filter here. And then again we will this is already negative. We will change the voltage so that current becomes 0 again. So it is near 0 now. It is 0 now. Then again we can flick it to the voltage display unit, and then see how much is the voltage. So this much is the voltage for this particular filter, and so on. So we can repeat the process for all other 3 filters also, and then note down the stopping potential corresponding to all the frequencies. We can repeat this by changing one more position, say 30 centimeters. This is the observation table for it. So we can write it for all the filters. For reds, the frequency is written, and then for what is the stopping potential for it, for so on. And then we can change the distance from 40 to 30 and then observe the same thing. This is how we do the calculation. So we plot a graph Vs versus frequency, and then we find out the slope of the graph, and then we can find out the Planck constant, as I have already discussed. So this H is equal to E delta Vs upon delta nu. So that we can calculate with the help of this graph, as it can be seen that delta V upon delta nu. So this will give us the slope, and then we can find out the value of H. Substituting this we can find out H, and the standard value of H is 6.62 10 to the minus 34 joule second. Again, from this graph only we will see the intercept on y-axis, so that will give us the work function. So we can find out work function as well as H from this. Now comes the second part. So for verification of inverse square law, if the intensity of illumination is measured in terms of current, then Ki is equal to L upon R square, where L is the luminous intensity and R is the distance of the point from it. So from this we can say that the graph between 1 upon R square versus I should be a straight line, which verifies the inverse square law. So to verify this, in this setup, the whole setup remains the same, except that this voltage is now given with positive sign, and then we keep voltage as constant. We can put a filter here and then apply a constant voltage to it. For example, in this case I apply a voltage of 0.50, say. So 0.5 volt is applied. This will remain constant throughout the experiment. Then we will switch on the our light source. Now this knob will be to the current, because we will be measuring current with respect to distance. So now we will change the position of our light source with respect to our photosensitive plate. So we can change it here from here. Again we change it and then note down the current. Voltage should remain constant. Then again change it and then note down the current, and so on. We can take 4-5 readings like this. Then we can repeat the same procedure for a different filter. So again we can take the value of current at different positions. This procedure can be repeated for all the filters or for at least 2 filters. Now let me tell you one thing, that when we have to switch off the device, we will first put this light source to 0. Then we'll put this voltage adjusting knob to the minimum or 0, and then only we can switch off the device. This is the observation table for inverse square law. So we take one filter and then take the values of current at various distances. That procedure can be repeated for the another filter, and then a graph I versus 1 upon R square is plotted, which should be a straight line, and it verifies the inverse square law. Let us discuss some precautions. So this instrument should be operated in a cool, dry and indoor space. Photo tube should not be exposed to the direct light, and this instrument should be kept in a dust proof and moisture proof environment, and if there is any dust on the filters, they should be cleaned with the help of some alcohol or so. The color filter should be stored in a dry and dust proof environment. And once you finish the experiment, put all the knobs to minimum and switch off the apparatus. That's all about it. Thank you and have a nice day.